Hi everyone. In this video, we are going to talk about text generation before transformers. So before the advent of transformers, text generation was primarily handled using traditional neural networks. These neural networks typically employed fixed size windows to process sequences of text, meaning they could only consider a limited context at a time. This approach often led to challenges, especially with longer sequences, as the model struggled to retain and utilize contextual information from earlier parts of the text. We are going to talk about how do we mitigate such challenges and what are the limitations to generation text generation before transformers. So let's begin by understanding how do we generate text. The game changer is probability, right? If I have a word I, another word want, another word to, another word bake, this makes a sentence I want to bake. Can I predict the next word after bake given a sequence of words or given a sequence? This is called a sequence. I can say I want to bake tomorrow, right? That could be an answer. All right, so the next word being tomorrow can be predicted using a probability score. Let's say it got probability score for today as 0.1, for tomorrow is 0.7, and maybe day after tomorrow, let's say day after tomorrow, right? It's 0.2. So definitely it's going to be tomorrow because the probability is higher for the word tomorrow, right? Let's look into it in more detail with a different example. If you see the step one, where we are talking about the man is walking down, right? The man is walking, the predicted word is down. The man is walking down, the next predicted word is the, and the man is walking down the street. This is the next word predicted, and then it ends with the full stop, right? So this is a seed of sequence of words that are fed in, and we are able to predict the next set of words. As I said, before the advent of transformers, text generation was primarily handled using this traditional neural networks, and these are basically based on a fixed window size to process sequence of text. Now, this is primarily what we are talking about is the problem before the transformers architecture. If we use a normal neural network, we would need a window of fixed size to predict the next character or word. But in text, sometimes the core meaning comes at the end, however long the sequence is, isn't it? If I have a lot of sequences, the meaning may appear here at the end of all of the sequences. Let's look at these examples. Hospitals are sued by 7-foot doctors. Local high school dropouts cut in half. Doesn't make sense. Funny, right? So these problems are, and for normal neural network, because they cannot remember stuff, they cannot remember long sequences. They cannot remember long sequences, and hence there is a problem. How do we solve this problem? How do we actually pass a longer sequences? We can do it at a character level, passing a state to a different neuron and the next neuron and so on. Just look at this example. I have a word T passed to a neuron. The context, it generates a context. This context is passed to the next set of neuron or model, and the next set of model, and next set of model, and so on. This is a very much like a passing memory. So the key is to pass the state as input to remember, right? Okay, so as I said, to mitigate this problem of not remembering the context at a time, and also it's limited to remember the context at a time. We utilize fixed size windows that created a lot of challenge. Researchers turned to recursive neural network RNN. RNN introduced the concept of passing information from one step of sequence to the next. Passing information from one step of sequence to the next. That's the beauty of RNN. Effectively creating a form of memory. However, despite these improvements, RNN still face significant limitations in maintaining long-term dependencies due to issues like vanishing gradient. Vanishing gradient. All right, so I will talk about these little bit and what are the mitigations for solving RNN's vanishing gradient problem. But let's look at RNN in overall understanding. So recursive neural network or RNN were significantly step forward in handling sequential data. I saw a cat is a sequence, and thus it's a sequential data. Right? So I said RNNs were significant step forward. Unlike traditional neural networks, RNNs have loops in their architecture. The loops helped in allowing information to pass to the next set of neurons and so on. So they work by taking in input data sequentially, with each step's output being fed back into the network as an input for the next step, and so on. This structure helps the neuron retain information over time, making it more suitable for tasks like text generation, where we are trying to generate the next set of word, right? Or also understand context and maintain coherence across longer sequences, which is a very crucial work for text generation. Now, as I said, despite their advantages, RNN still struggled with retaining information over very long sequences. The challenge was that as the sequence length increased, the network's ability to connect earlier information with later information diminished. The network's ability of not remembering so long contexts was a problem. And this is where more sophisticated variation like LSTM came into picture. LSTM and GRUs came into picture. All right. So what is LSTM? What is LSTM? It's an advanced version of RNN, obviously. Long short-term memory network or LSTM were developed to address the limitation of standard RNNs. Limitations of standard RNNs. LSTMs introduced a more complex architecture with a series of gates. So you can look at some of these gates that were introduced in LLM. All right. So the input gate, there are different type of gate. I mean, I would discuss like input gate. There is an input gate. There is a forget gate. There is a forget gate, and there is an output gate. There is the output gate, right? Input gate, forget gate, output gate. LSTM introduced a more complex architecture with this series of gates. These gates control the flow of information, allowing the network to maintain and update its memory more effectively. Unlike RNN, we do not have any control, thus we have to capture each and every information that we pass in as a sequence to the model. The forget gate, which is a feature that allows the LSTM to decide what information to discard from the cell state. The input gate determines what new information to store and the output get controls what part of the cell state to output. This gating mechanism enables LSTM to retain important information over longer sequences, making them particularly effective to tasks requiring long-term dependencies such as text generation, translation, speech recognition. Right? So LSTM was much more advanced than RNN and was a good model for text generation and much more. The next model is GRU. Gated recurrent unit or GRUs are simpler alternative to LSTM introduced to reduce the complexity and computational cost associated LLM. What do we mean by that is GRUs combine the forget and the input gates into a single update gate and merge the cell state and hidden state into one. If you look at it, there is no cell state in GRU. We merged it. This streamlined architecture makes GRU less computationally intensive while still effectively managing long-term dependencies. So GRUs maintain similar performance to LSTMs on many tasks but with fewer parameters and faster training time. Their simpler architecture or structure, I would say, is an efficiency or bringing efficiency to make them a popular choice in various sequential data application, text generation, including text generation, where they help maintain context over longer sequences. So longer the sequences, the better the responses or generation is. In summary, I can say before the introduction of transformers, text generation relied heavily on recursive structures to manage and retain context over sequences. Techniques like RNNs, LSTMs, and GRUs, each of them brought their advancements, enabling models to handle sequential data with increased complexity and effectiveness. These advancements laid the groundwork for modern text generation methods, allowing for automated tasks as creating rental ads and simplifying user experiences. By understanding and applying these foundational models, we can appreciate the evolution of text generation techniques and the significant improvements brought by contemporary architectures like transformers. With this, I would like to conclude here. In the next module, we are going to deep dive about transformers. Thank you, everyone.